We have talked about the logic that is involved in the rain shadow and using the dry adiabatic lapse rate, the dew point lapse rate, the moist adiabatic lapse rate to go up the windward side of the mountain that's associated with the rain shadow. And then we've talked about the logic of using the dry adiabatic lapse rate with the dew point lapse rate to add degrees Celsius and to add heat to the parcel on the leeward side of the rain shadow. So now we understand the logic of what we're doing. Now we can apply some numbers to it. And this directly goes to your assignment on rain shadow because it's such an important topic for understanding climate and for understanding climate changes. So we look at this in 5 steps. And the first step is that we start on the windward side of the mountain and we start at the surface level. We start with an imaginary parcel that's gathered at the ground at the environmental air temperature, which in this case is 20 degrees Celsius. And we also measure the dew point and the actual vapor pressure of a parcel at ground level. And then we start another imaginary parcel at the dew point at ground level. This dew point is at 12 degrees Celsius. So it's a bit of a humid parcel that we're sending up, but it's coming off the ocean anyway, so that makes sense that it would have a lot of water vapor in this parcel. This dry adiabatic lapse rate for the dry parcel will be a 10 degrees Celsius per 1,000 meter drop. The dew point adiabatic lapse rate will be a 2 degrees Celsius per 1,000 meters drop. So when you get up to 1,000 meters, your environmental temperature is going to be 10 degrees Celsius. Your parcel temperature is going to be 10 degrees Celsius. And your dew point temperature dropped 2 degrees, and it's also going to be at 10 degrees Celsius. You have the base of a cloud because your dew point for your parcel is matched by your parcel temperature. So here is your LCL or base at 1,000 meters. From here on out, this parcel will be continuously condensing. It will use another lapse rate, and that is the moist adiabatic lapse rate, which is, I already went past all that. I'm on this one already. The moist adiabatic lapse rate is 6 degrees Celsius drop per 1,000 meters. So if we are at 10 degrees Celsius at 1,000 meters, then this parcel is going to be 4 degrees Celsius at 2,000 meters. We took off 6 degrees Celsius. We are no longer using the dew point adiabatic lapse rate after condensation. The reason being is we want to keep this parcel continuously condensing, and so we have the entire parcel dew point matches parcel temperature, so we can continuously condense as long as we have vapor available. So in terms of that, at 2,000 meters, we have 4 degrees Celsius for the temperature of our cloud. 4 degrees Celsius is above freezing, so this cloud would still produce, if it went into precipitation, it would still produce rain in this area. This is why we have redwood forests on the windward side of the Sierra Nevadas in California. A lot of rain in this area. If we go up to 3,000 meters, we are losing another 6 degrees Celsius, and we go from 4 degrees Celsius to negative 2 degrees Celsius at the top of the mountain. And you continue that lapse on the moist adiabatic lapse rate to the top of the mountain. When we get to the top of the mountain, this parcel, which started at the surface and was warm, did rise, did expand, did cool, did become more dense at the top of the mountain. it has rained down quite a bit and lost much of its water vapor through precipitation on the windward side. When it is becoming more dense with the cooler temperature within the parcel, it starts to sink. It starts to sink already drier than when it started at the other surface due to the rain. And as it sinks, it moves into a higher atmospheric pressure, which is pushing and contracting our imaginary parcel. And in doing that, we have a lot more movement of the molecules and warmth in that area. We are now descending the Rockies using the dry adiabatic lapse rate of 10 degrees Celsius per 1,000 meters, except now we're adding temperature as we go down the other side. So -2 plus 10 equals 8 degrees Celsius at 2,000 meters. On the other hand, we look at the dew point parcel as well. That dew point parcel was at 100% water vapor. It might have lost 2 or 3% water vapor, so it is going to descend at a dew point adiabatic lapse rate of adding 2 degrees Celsius per 1,000 meters. -2 at 3,000 meters becomes 0 at 2,000 meters. If we go down to the 1,000 meter mark, we are adding 10 degrees to the parcel for 18 degrees Celsius. We're adding 2 degrees to the dew point parcel for 2 degrees Celsius. Then we come down all the way to sea level on the leeward side of the mountain, and we've got another 1,000 meters, another 10 degrees Celsius for the temperature of the parcel, and we've got another 1,000 meters, another 2 degrees Celsius for the temperature of the dew point parcel. That is a very big difference now between the ambient temperature, the environmental temperature, and the dew point temperature on the leeward side at sea level. That very big difference signals dry air. And that dry air means that you have a very warm, look how much warmer it is, a very warm parcel in this valley that is very dry, leading to desert conditions in the valley. In terms of that, I talked about that here, about compressing this air. The compressional warmth of this descent effectively vaporized off any remaining water vapor in the dry parcel that started with 1 to 4% water vapor, lost a lot of it in the precipitation, and then came down and the rest of it was vaporized essentially by the warmth of the parcel as it descended. On the other hand, that dew point parcel started out at 100% water vapor, maybe lost 2 or 3%, and then came down, and it still has 97, 96% water vapor in that water parcel, in that dew point parcel. So that is the calculation that you'll see, and you'll be looking at your homework to determine what the numbers are and what types of precipitation fall where along this mountainous hillside. So to sum it all up, we have looked at environmental lapse rates to predict stability of an atmosphere. Then we've looked at 3 other different types of lapse rates: the dry adiabatic lapse rate, the dew point adiabatic lapse rate, the moist adiabatic lapse rate, to determine things like cloud base or lifted condensation level, and to determine the temperature inside the cloud with the moist adiabatic lapse rate. I hope this helps you out with your assignment, and you can use MS Teams to work on this together with your group. See you on the next video.